Hi, I'm going to try the trail problem from your midterm, and I'm going to sort of try to do a dry run as if I've never seen this problem before. Disclaimer, I have seen a problem. I haven't actually tried it though. I don't know what the answers are, but I'm going to sort of simulate seeing this problem for the first time and going to try to talk through my thought process as I solve it. And, I may make mistakes. Hopefully I don't. And then at the end, I'll just check over my work and clarify any mistakes I might have made. All right, so I'm kind of excited. Let's jump into this. So, all trails lead to Rome. A trail is a tree. Exactly one of the child nodes of each non-leaf node. I'm already confused. So child node of each non-leaf node has a label. The child's label equal to the label of this node. Okay. Exactly one. It's probably important. Alternatively, so giving another definition, okay? Is this another definition or like another condition? I think it's probably another definition. A trail is a tree where every node, okay, so I'm at a node, has a singular path from this node to a leaf consisting entirely of the nodes with the same label. So do I have a path to a leaf with all fours? Oh, okay, this is actually as bad as I thought. So does every node have a path to a leaf of just itself? So one, cool. Okay, it's not too bad. Does that make sense of the first definition? Exactly one of the child nodes of each non-leaf node has a label equal to the label of the node. So if I'm here, exactly one of my children can be equal to me. And here, exactly one of my children can be equal to me. Okay, actually not as bad as I initially thought. Cool. Generally, before I actually look at the skeleton, I like to sort of frame an approach. I guess the main thing I'm not too sure about right now is like what the base case is. So this is a path problem, right? I am trying to enforce some condition from the root to a leaf. So I probably need a condition here just to know when I've hit the end of my path, because like that's why I need to make a decision on whether this was a trail or not. So if it's a leaf, my gut instinct is that like if it's a leaf, like the simplest info is just like a 1, right? And I'm guessing this is a trail. Do they have a doc test for this? Oh, nice, they do. Okay, so that just gives it away. So right, if we just have a leaf, this is a trail, which I guess that makes sense because it's not included in the definition. So if this was false, then like that would just break everything. Like nothing would ever be classified as a trail. And yeah, I mean that makes sense because we're saying for every subtree is also a trail. So this is a trail and this is a trail. And if this is a trail, then the leaves have to be trail. Okay, cool, that makes sense. And then I had to somehow mandate this like only one condition from the perspective of each level. But then I also have to make sure that every single one of my subtrees is also a trail. It's not too bad. This is I think it's too unique of a structure. So I probably just have to return like that all of my subtrees. I'm going to iterate through all my branches and check that all of them are trails. This is a Boolean expression, right? A Boolean function. Yeah, okay. I guess, I mean, I know if it's a leaf, it's a trail, which has to be true because we have leaves here, and I guess they have to be a trail. And then I have to somehow do the check 1, and then after that, I just make sure all of my subtrees are also trails. Okay. Doesn't sound too bad. Let's try to implement this. Like I said, they basically gave away with this doc test here. So, yeah, if it's a leaf, it's a trail. If true, return true doesn't even make sense. So yeah, if it's a leaf, this doesn't make sense because branches, well, I mean, leaf is not branches. So this will give me the opposite of what I want. So not branches makes sense. Or if branches is empty, which is equivalent to being a leaf. Okay. B. Okay, match one. I guess this is where we're checking the like single path condition. I don't really know what's going on here. It has to be equal to 1. Let me just look at my options. I don't really know what's going on. Okay, so some function here, and then we're checking if it's equal to 1. So obviously I can't use a Boolean aggregator. Right, that doesn't make sense. Okay, I'm not going to compare true to 1 or false. I mean, I guess I could, but I don't know if that makes sense. We could come back to this. Why did I circle them? We'll come back to that thought. Just cross them out for now. When, min, max. I mean, I can't make the max or the min of booleans or some booleans. When, does that make sense? Wait, okay, so what does this list comprehension give me? This list comprehension gives me every tree within branches if some condition. Okay, so this is gonna give me a list of branches, a list of trees. Tree. So yeah, I mean, I guess it doesn't make sense to take the max, min, like sum or anything. I guess I'm just gonna count the number of trees that fulfill some condition. So I'm going to filter out the trees that don't meet this condition, and I'm just going to finally count how many trees do. And I guess the condition is that, like, from the perspective of one node, only one of my child will be equal to me. So that's a condition of being equal to a child. So that should just be labeled T, which is me, is equal to label B, which is my child. And then only one of these can happen at each level. Cool, that makes sense. And what's D? I mean, this should probably just go here because, I mean, if this is a Boolean value, then I have to use it somehow, right? So, or is it match one or is it not match one? I mean, it's match one. Only one of my childs should match. Cool. And then, oh yeah, this is just the recursive call. So this is what I was just thinking before, right? It says that all of my or do all the trees have these subtrails? Well, if there's one path from every node to the leaf that fulfills this condition, then that's the definition of a trail. So every single node has to be also a trail. Every subtree is a trail. So I just have to mandate that condition that all of my so this is match one, then I have to mandate that all of my subtrees are also trails. Okay. Let's double check. I don't think that one was too scary. I'm not going to spend too much time checking because time is important. The leaf, not branches, empty branches, life. All right. Okay, let's try B. Trail. Implement max trail, which takes in a tree and determines the highest number of nodes in a trail that is a subtree of T. The following diagram displays a tree, which is not a trail. Yeah, so for some reason, the tree itself doesn't have to be a trail, but it determines the highest number of nodes in a trail that is a subtree. Okay, so I'm going to call it subtrails. The highest number of nodes in a subtrail. Okay, so if my branch is a trail, so this is not a trail, so that's not good. But if it is a trail, because it says 4, 4, 4, I'm just going to return the number of nodes here, which is 4. Okay, I mean, I don't really know where to get started this problem, so I think just peek at the skeleton. This will be a counting problem. Okay, yeah, I see the common sort of patterns in counting problems. I return 1. We're going to increment our counter here. And then we're going to return max between my branches, I guess. Okay, so this is probably the leaf condition, but if it's a leaf, return 1. That makes sense, right? Because if it's a trail, I should return 1. Did he give us any tests? And so if it's a leaf, I return 1. Yeah. I mean, because if it's a leaf, it has to be a trail. And a trail of just itself will, the max trail is just 1. Or wait, in a subtree of, I mean, if it's a leaf, it can't have any subtrees, so is it 0? Is it 0 or 1? No, wait, no, they tell us it's 1. Let's go with my gut and say if it's a leaf. If it's a leaf, it has to be a trail. All right. Else, this is here where we're going to be aggregating our count. I mean, we don't. Why are we doing work at this level? Because I don't count myself in, right? I just count my subtrees. Highest number of nodes in a trail that is a subtree of T. Is T a subtree of T? Do you give us any help for B? They do not. I'm gonna look at C. Okay, I mean, these look really similar. 1 plus. Okay, so I mean, this is just, again, summing trees again. That doesn't make any sense. Here, we're counting the number of trails. 1 plus num trails. Does that make sense? And then I recursively keep returning the number of trails. I mean, I guess that does make sense, right? Because each of these are individually also trails, so I am counting trails in a sense. Do you have options for D? Nope. Okay. I mean, okay, so I mean, I guess just to talk through what my conditions are to figure out what the elif and the else are. I mean, there can only really be 3 cases here, it seems, right? It's either a leaf, it's not a trail, or it, like, is a trail. Or just something like this. I don't really know if we should return 1 or 2. Do you give any examples? Here they have 1, 2, 3. Return 1. 1, 1, 2, 1. Okay, this is exactly what I want. So the question is this going to return 3 or 2? Oh, why does it return 5? Okay. 1. Wait, there's only 5 nodes. I mean, so I guess this whole thing is a trail. So I'm just going to return 5 in total. I'm just going to return every node. I think... Okay, so I guess T is a subtree of T, I guess. Whoops. Okay, so that helps. Okay, I think things make sense now. So like if the current node I'm at is a trail, then I'll just return myself 1 plus the number of nodes in my branches. Okay. And then not the max, right? Because I don't want to like choose between 3 or 1. I just want to sum it all together. So I'm thinking of sum. Yeah, I don't take the max length, the number of max trails. This doesn't make sense because then you're just counting trails. I like sum. I like that they give us 2 options for sum. It hints to me that probably is sum. We're just counting. Because I think we're going to sum together all of the maximum values. So does that make sense? So if we're at 1, the max would be 1. If we were at 2, the max would also be 1. No. So 1 would return 1 because it's a leaf. 3 would return 1, and then so we're going to sum these together for 2. And then 1 is also going to add itself onto the 2, and that gets us to 3. Okay, I think it works. I think I'm going to run out of time if I keep looking at this one. And if it's not a trail, then that takes us back to the first case. I just take the max of my branches. I'm going to take the max of my branches for B in branches of T. Okay, I'm back. So I just looked at the solutions. Fortunately, I did get this problem right. Hopefully me talking to the thought process was helpful. There were a lot of like different decisions I had to make, but hopefully you can see that like I'm not confident throughout the process. I just kind of grab onto an intuition, hold on, and try to add on more info until I can finally get to an answer. I don't think there's too much to explain here because I think most of my reasoning as I was solving it was correct for the most part, but I will just a little more in depth talk through some of maybe the confusing parts. So this leaf condition, we're not on max trail. So let's start with is trail. I know a leaf has to be true. This should make sense because if it's ever the case that I get down to a leaf, that means I've completed my path. If I was able to successfully get to a leaf without someone screaming at me that you're not a trail, then that means I am a trail. Okay, and they don't include the leaf in the definition. Otherwise, I think I explained the core logic of this problem, right? We want to be checking if A, one of my children is equal to me, and B, all of my branches are trails, and we can deduce this condition because they tell us that of each non-leaf node has to fulfill this trail definition. So it's a recursive definition. I'm saying every single branch, within every single branch, within every single branch, within every single branch, all have to be trails. Okay. For max trail, this one was definitely a little tricky. yeah, this if-lease condition, again, it's really helpful to look at doc tests, right? That was something that helped me out consistently. Yeah, I think this condition is the hardest one here. But I think once you're able to separate out, okay, so this is the case where the label I'm at is a trail, in which case I would need to append on the 1 to include the root of the tree I'm at, plus all of the nodes in my branches. And then here, we're not including myself, so I just take the max. All right, so like, if this 1, if I'm saying my whole tree is a trail, then that's equivalent to summing every single node in my tree. Whereas if the node I'm at is not a trail, then I have to take the max of each of my trails. So that's actually a pretty nice problem. That's a pretty clever decision to ask all of you to have to make on the exam. It's definitely a little tricky. Let's just prove to ourselves that it works. So let's use this tree. So I'll do it more neatly now that I'm out of exam mode. 1, 1, 1, 3, 2. Okay, so since this entire tree is a trail, I just want to sum every node. Okay, so I'm going to do, I'm going to add 1 to factor in this node, and then I have to count all of these. And all I have to do is I have to just sum the max within each of my subtrees, okay? So if I try to call max on this subtree, that's going to call max on each of its subtrees, and then this would return 1, and this would return 1. And then we're going to sum these two values together, and that gives me back 2. And then finally, I just have to add on the +1 to factor in the node I'm at. So, right, the final output for this is going to be 3. And then this is just a leaf, so it's 1. Right, and then that gets me to 5, which is how we arrived at the stock test. So I didn't really have, on the exam, I made the decision to not go through this whole proving it to myself, because it can be really time costly, and if you spend too much time on that, then you sacrifice other points potentially. So I wouldn't recommend always trying to prove something to yourself on an exam. If you don't have time, just follow the intuition sometimes, but you know, it's your choice. I'm not going to tell you how to take your exams. So yeah, hopefully that was helpful.